At this point in our journey through quadratics, we're finally ready to do some graphing. The issue when we get to this point, though, is which form of a quadratic should we use for graphing? Well, one option would be to simply leave every quadratic function in its initial form and use that. However, this strategy would make it very challenging to make observations about shapes and patterns in quadratic graphs. So in order to facilitate conversations about shapes and patterns, this video will focus solely on quadratic functions that are in the vertex form. Sure, not every quadratic function you are given will be in the vertex form, but that's not an issue since we already know how to convert any quadratic into the vertex form. Thus, let's begin graphing quadratic functions in the vertex form. We'll start things off with the simplest case of the vertex form, f of x equals x squared. This is the quadratic parent function, and as such, this will be a good place for us to establish the key values that we'll use when graphing quadratics. Let's start by trying out the same key values that we used for absolute value functions, the integers from -3 to 3. Then, as we evaluate the function to get each output, we'll also plot the resulting points on our graph. Eventually, we get these 7 points. From there, it might be helpful for us to plot a few more points and make a few observations. We'll start by plugging in 4 and -4, which both give us outputs of 16. And notice that these points are already off the screen, so we don't need to worry about plotting them. In fact, as you get further away from 0, the outputs will continue increasing. So for this situation, we don't have to worry about any integers beyond what we've already covered. It might be nice, however, to get some intermediate points on our graph. So let's plug in these 6 numbers to see what's going on in between the points that we already have. As we plot these new points, we can really start to see the details of the graph shape better. The main area to observe is the bottom of the graph, which is called the vertex, just like it was in absolute value graphs. We can see that the graph is going downhill as we approach the vertex from the left, but then the graph switches to going uphill as we continue moving to the right. The big difference from absolute value graphs, though, is that our graph here doesn't come to a point. Instead, it makes a smooth transition from its downhill phase to its uphill phase, as we can see if we continue plotting points to fill in all the holes in our graph. Once we do that, we can officially see the final shape of the graph, which is called a parabola. One key feature of a parabola is the vertex point that we just discussed. In this case, the vertex is at the origin of the graph. Another key feature that we've already mentioned is the fact that the graph is going downhill when x is negative and is going uphill when x is positive. We can formalize this language a bit by saying that the function is decreasing when x is negative and increasing when x is positive. Our final key feature, which we haven't encountered before, is the lack of straight lines. Thus far, we've discussed graphs of linear functions, which are definitely straight lines, and graphs of absolute value functions, which are just composed of portions of 2 straight lines with endpoints that meet at the vertex. This parabola shape, however, doesn't have any straight lines. Instead, it's a curved line, or just a curve. Because of this curved shape, a parabola is often referred to as U-shaped, which contrasts it nicely with the V shape that we used to describe absolute value graphs. Now that we know more details about the shape of this graph, we're in a better position to decide what our key values should be. And to do that, We just need to decide which points we need to plot here to get a good picture of the graph. Thankfully, this is a pretty easy conversation for the quadratic parent function because we can simply use the 7 points that we started with. We do have to be slightly careful around the vertex area and remember that the vertex area should be a smooth curve rather than a sharp corner. But as long as we remember that, these 7 points should be enough to give us a good picture of the graph. Therefore, our key values for quadratic functions will be the integers from -3 to 3, the same as they were for absolute value functions. It's now time to explore more complex cases of the vertex form. We'll still avoid having an a value for now, but let's jump right into including values for h and k. We'll do this with the function g, which we'll define this way. But before we try graphing g, let's quickly graph the parent function as f with color-coded inputs, similar to what we did when working with absolute value graphs. Then, we're ready to make our extended table of values for g, which will look like this. From here, we should think back again to our work with absolute value graphs and recall that we want our 7 key values to show up in our extended table right before we apply the parent function. Of course, the parent function is different now, but the concept applies nonetheless. From there, we can easily complete the table moving to the right, and with a little bit of inverse operation analysis, we can see that we need to add 3 to each of our key values to get our key inputs. Once we have our key inputs and the corresponding output for each input, we're ready to plot our key points. These key points should fall into a familiar pattern that we can recognize as the beginnings of a parabola, and we'll even graph the core of that parabola right now. However, depending on the level of precision that we're going for, we might want more information about the shape of the graph as it extends further up. To get this information, we just need to broaden our inputs slightly to get a couple more points, and once we have those points, we can extend the graph with more confidence. These final couple points won't always be necessary, but they were probably a good idea in this case since we're still developing our understanding of parabolas. And with that, we've completed our graph. Now for a bit of analysis. We've already established that this graph is still a parabola, but the location of that parabola has changed. But why did it change? Well, recall that the -3 inside the parentheses of our function definition meant that we had to add 3 to all our key values to get our key inputs. This shifted the parent function 3 units to the right. Then, the -7 outside the parentheses in our function definition caused all the outputs to be 7 units lower than they were after squaring. This shifted the graph down by 7 units. This sort of analysis shouldn't be anything new since we've done this process many times before with graphs of absolute value functions. Still, it is good to confirm that the same principles apply when working with graphs of quadratic functions. For our next function, let's consider a different g defined this way. We'll once again start by graphing the parent function and making our extended table of values for g. Then, we'll fill in our key values and complete the table, moving to the right and to the left. This gives us these key points, which we can complete with this graph. Now, the way that this graph was transformed from the parent function shouldn't come as a surprise. But let's take a moment to think specifically about how these translations affected the vertex of the parabola. In the parent function, the vertex is located at the origin. But after the graph shifted 5 units left, the vertex moved to this new point. Then, the graph shifted up by 2, which moved the final location of the vertex to this point. Now, if we compare the official vertex form to g of x, we can see that h is -5, since x minus -5 is the same as x plus 5. We can also quickly see that k is +2, which means that the values of h and k in g tell us exactly where the vertex of the parabola is going to be. This illustrates why the vertex form is called the vertex form, because of the information that the form provides us about the location of the vertex in the function's graph. Our next example is going to include a value for a. And while we will still fill out an extended table of values eventually, let's start by making a guess at what this graph will look like. First, we know from the values of h and k that the vertex of our graph is going to be at the point -1, -8. So let's shift our parent graph accordingly. Then, we have to take the value of a into consideration. And since multiplication by the a value occurs after the squaring operation, we know that the a value will stretch the graph vertically, which might make the graph look something like this. From there, let's find some points on the actual graph by filling out our extended table of values. We can once again fill in our 7 key values just before the squaring step. Then, after we complete the table in both directions, we can plot our key points, or at least most of them. The points that correspond with our key values of 3 and -3 will be well off of the graphing area, but at least that gives us an idea of how quickly this graph increases as we move away from the vertex. Then, we can see that our previous guess at the graph is pretty accurate, but we can now update that guess to be even better by aligning our parabola with the key points. One final note about our graphing process here is that we didn't necessarily follow our established transformation procedures very carefully when attempting to guess what the graph would look like. Typically, vertical stretches would stretch away from the x-axis, but in this example, we simply located the vertex and did sort of a pseudo-stretch to guess the final shape of the graph. Thus, let's do one more graph of a vertex form function while following our typical transformation procedures. To start that process, let's make an extended table of values for this function and label the columns appropriately. Then, we'll fill in our key values and their squares, but we'll stop filling in the table there for a moment. Instead, we'll label the transitions from one column to the next with the operation that's occurring. Looking to the left of our key values, we can see that we're subtracting 4 from our first column to our second column. This means that we're adding 4 as we go the other way. Then, let's go to the rightmost column that's filled out and identify the operations moving forward from there. Here, we can see that we're first multiplying by -2, and then we're adding 6. For our graphing process then, we'll start with the graph of the parent function in pink, and then we'll look at our horizontal transformation. Since the translation to the right is the only horizontal transformation occurring, we don't have to worry about the order of the transformations there. We can just shift our graph 4 units to the right and move along to our vertical transformations. Here, though, we do have to pay attention to the order. Since the multiplication by -2 is closest to the squaring operation, that's the first transformation for us to consider. But as we've seen before, that multiplication by -2 can itself be thought of as 2 transformations. First, the 2 is going to stretch the graph vertically, so let's perform a dilation with a scale factor of 2. And notice here that we are indeed stretching away from the x-axis now. After that, though, we need to incorporate the negative aspect of the -2. This is going to result in a vertical reflection over the x-axis, which will look like this. Finally, we can take the addition of 6 into account. This is going to shift our graph vertically, so let's perform that translation of 6 units upwards. This gives us what should be our final graph, so now we can complete our extended table, plot the points we get, and see that our final blue graph was correct. This more formal application of transformation rules may have taken some extra time, but it is good to remind ourselves of this process and get some extra practice with it. When we graphed absolute value functions, we eventually got to a point where we introduced a more official transformation format, which looked like this. If we adjusted this format to include squaring as the parent function instead of the absolute value, we would get this as the official transformation format of quadratic functions. Notice that this transformation format looks a lot like the vertex form, except that it has a horizontal scale factor included as well. This raises the question, why doesn't the vertex form include the possibility of a horizontal dilation? In order to answer that question, let's look at one final problem that has a horizontal dilation. We'll graph this function based on an analysis of the transformations occurring, and early on, we can see that we do indeed have a horizontal dilation. Then, if we continue on from there, we eventually get this graph. And completing our extended table of values confirms that this is indeed the correct graph. However, there is another path for us to explore if we try to convert this function into the vertex form. Typically, we would start that process by converting our function definition into the standard form. But in this case, we don't even have to go that far. If we write the squaring operation as repeated multiplication and perform that multiplication, we can see that the denominator inside the parentheses can easily be removed from the parentheses. Then, instead of dividing by 9, we can multiply by 1/9 to get this expression, which just so happens to be in the vertex form. From there, we can do the graphing process again with a slightly different set of transformations, but we end up getting an identical graph. It turns out that any horizontal dilation of a parabola can be rewritten to be part of the vertical dilation. This is why the vertex form doesn't include the possibility of a horizontal dilation, because it can always be reworked into a corresponding vertical dilation. That concludes this video on graphing quadratic functions in the vertex form. Hope you learned something new, and thanks for watching.